of electronic lab, and I'm there. It's such a wonderful lab. And doing
Thank you, Professor Chen. Sorry for the glitch. I think we lost about 5 minutes. Yeah. I'll try to speed up. Okay. And you know, it's never ending. I cannot come out a better title than this. But I did come out a worse title. So I feel like my job here is today to stir you up and probably get you out of your comfortable zone and do something probably revolutionary. We'll see, and whether you can get some resonance from me. I would like to thank Professor Chen and to give me the opportunity to talk to you. And thank you all for coming, and I need to thank another guy for not coming so I can talk. So thank you, God, the professor. And so it's not a coincidence, right? Today we are here together and learn something, but I actually can stop talking if you have seen this slide. It's already, the book is already there. Second edition is 2014 already. There's in 2000, there's a book about applications of fractional calculus in physics. In 2014, 2011, that's 10 years later, and fractional calculus, introduction for physicists. I met this guy in person. He was a plenary talk for the Catania 2014 International Conference on Fractional Derivatives and Application. So it's in Catania in Italy. So basically, he gave a talk and a very compelling reason that why physics should embrace fractional calculus. But I'm not a physicist, but I'm living in a physical world. So I'm going to show you a little bit more. So you can see people around the world is trying to work on different aspects and try to apply fractional calculus into almost every subject. So you can see the fractional order calculus not only for physicists, it could be for scientists and engineers. And talking about dynamics could be fractional order. Even talk about nuclear reaction dynamics is actually fractional calculus. In there, this is a 2015 book. This is a recent book as well. All that maybe is 2013, 2014. If we check more, you can see fractional calculus in the solids and about anomalous charge transport in semiconductor and dielectrics and nanosystems. I know many of you are doing nano level work. And so for quantum mechanics, using a fractal and a fractional calculus point of view, this is an old book. Francis Maynardi, the second author, he visited UC Merced in 2013. And Richard Megan also visited UC Merced in 2014. And I invited him to give a talk, 13 actually, sorry. So fractional calculus can be used in many other aspects like thermoelasticity. This is a very recent book. And fractional Fourier transform, this is a quite old book. And also talking about physics of fractal operators, okay? Yes, Bruce West, and he also visited UC Merced, okay? And not just because of me, but because of our new university, they want to take a look. So for us, we also did something. So these are all from our group, and about systems and controls, signal processing, and motion controls. Okay, think about you can move around. Probably is governed by fractional calculus. So do you believe that your muscle is governed by integer order model? Probably not. Probably is a distributed order. Okay, so we wrote a booklet to advocate this point of view. So the order could be continuum. Okay. So in fact, there's a very interesting slide talking about fractional calculus versus integer order calculus. You already probably heard that the differentiation and the integration could be of non-integer order, right? Non-integer order. So using a integer order model, you could talk about non-integer order model, and so on and so forth. So in fact, integer order calculus is like you need a set of ranges of different sizes to get the problem solved. But fractional calculus, you have those tuning knob. You can adjust it. So that analogy is pretty interesting to me. And in fact, we usually end up the talk here, and you will not lose anything. We can stop here. But if you want to zoom in a little bit, and I need to do advertisement of my lab a little bit, we have five aspects we do. A lot of people know our lab is a drone lab. We do use Merced as unmanned aerial systems to fly the aircrafts, to spy crops, not human. And so this is only one of the 5 areas we do unmanned aerial system. We also do cyber physics systems on renewable energy systems and electronic systems. And the last but not least is applied fractional calculus. We want to make sense of this differentiating and integrating of non-integer order. And to ask the question as an engineer, why bother? Okay? Can we harness, get something out of it, and do better than the best? That's exactly what I've been pursuing in the past 10 plus years. Before 1999, I never heard about this thing, fractional calculus. Okay? And even today, I'm still learning, and every day I gain more insights into it. So today, I'm going to share with you the fractional portion of my understanding of this insights of why the fractional calculus is an exciting topic, why you need it. So, but you may ask, as a lot of researchers in physics, what qualifies you to talk here in front of physicists? So, why you dare to talk, So I say, look, we have some common substrate we share. That is the complexity we have today. We're facing complex problems. Our complexity around us is getting higher and higher. But really, how you measure the level of complexity is not really solved, right? How to quantify it, how to characterize it, how to tell the stories, the full stories about complexity, it's not really solved. You agree with me? So it's a process we pursue the understanding of the complexity. So that's the reason we should talk to each other. Okay, the world is so complex. But there's a question valid saying that because it's complex, then what signifies a complex system? Okay, or what kind of signature you see, then you will say, oh, this probably is complex. So it turns out that is called a power law. So this is a very interesting thing. You can buy a bag. Oh no, it should be bigger. So it's the same. This is the same words here. I went to a physics conference, and all I got was a lousy power law. Okay. And also a template to produce a natural science paper. There's a template. Do you know that? It's here. So you find data second, you plot it on the log axis, then you what? A square, okay? I submit to nature. So that's basically you are facing a complex system, and you observe from outside, okay? It looks like there are power laws everywhere, okay? So you agree that our world is complex. So and you agree that you sometimes feel uncertain, unequal, and unfair of this world. So read this book. This book will tell you that it's inherent to a complex system to be uncertain, unequal, and unfair. Okay? So next time when you complain, say, oh, it's unfair, then the best answer you will receive is live with it. We are in a complex world. Right? So this is called the complex world ought to be. uncertain, unequal, and unfair. So I suggest everybody use this complex words point of view to handle our complex daily life. Okay, so you don't feel so angry. Okay, so the Bruce West visited our campus last year and gave a very interesting talk as well. It's recorded, also put on the Vimeo channel, and you can find out his talk.
Where?
The Vimeo. This MTS, Mind, Technology, and Society seminar series. And so that's the key message in this book. Okay, it will help you to understand the complex words in a fair way. Okay, in a fair way. So complex words, and the deeper message behind this book, actually, he's saying that to really understand the complex words, you will need fractional calculus. Okay? But don't worry, in the last slide, I'll show you something surprising. So this is a book 2-3 years ago. And of course, it's as usual, it's equation free. Okay? You don't have an equation there, so it's easy to digest. So this is the first book, okay, from my best understanding, to talk about complex words and its potential connection to fractional calculus. Okay? There are other books also trying to explain complexity, try to understand the complex words. So you can see the complex words, non-extensive statistical mechanics. They almost touched fractional calculus, okay, but not there. Almost touched. So those books, Duncan Watts, about the 6 degrees of separation and common sense fairless, and so on and so forth. And there's emergence of everything. So this word, I want to remind, from now on, you should consider how the world became complex because of the emergence, and the emergence is because of a fractional dynamics behind it. Today I'm going to convince you that. There are more. So like emergence of dynamic order, synchronization phenomenon, and in the complex systems, okay? Complex systems. So you can keep saying the complex. And the small words, Duncan Watts again. And those are also famous. Taleb, talking about black swan. He wrote a popular book called Black Swan. Black Swan, okay. Black Swan. So how to deal with the surprise, okay? So you will see surprise is linked to fractional calculus as well. Oh, here's a black swan. So this is the book he said is the impact of the highly improbable. So how these things are connected to fractional calculus, and these people never really touched the fractional calculus. So that's the key theme for today, okay? Also extreme events and so on and so forth. All these things like extreme events, like emergence, all these things are connected to fractional calculus. You are going to see that. And there are more. There's a new paper, 2015, talking about solar cosmic ray fluxes by the fractional derivative method. Of course, this is from Russia. And this is a very famous guy called Uchaikin, and Sibatov also. Very known name in the field. So you can see the dynamics of the Milky Way. I love this title. Okay. And discovery of cosmic fractals. So I think I leave you with an impression that fractional calculus is everywhere, but you are not convinced at this point, which is understandable. However, as early as the 1950s, Scott Blair already said that. Let me paraphrase what he said. Okay, we use integer order calculus models, methods to quantify the real world in front of us. It's only for our own convenience. Okay, our own convenience. The real system is actually not that way. Okay, it's not that way. So it's complex. The real world is complex, complicated, and running in a fractional order dynamic way. Okay? Using the integer order is just for an approximation. Okay? So because people didn't embrace fractional calculus, so they did a lot of detours. So all the stuff here are detours. Okay? Detours. Okay? Today I'm going to show you a direct path to it. So you don't have to make a detour. Okay? So this is also a detour, okay, to me. There's a book, 2009 Springer book. It's called Sociology and Complexity Science, a new field of inquiry. They believe everything is new. I cannot go through these details. So they start to form sort of complexity science and so on and so forth. And so emergence is here, system dynamics, artificial life, genetic algorithm, data mining, fuzzy logic, agent-based modeling, whatever. So you can see the different, but to me it's a detour, okay? I'll show you another picture later on, but I want to make my message right. What's beyond that? So they just like blind people and touching the elephant from different parts of the body. What's beyond that? What's the whole picture? My submission is we should use fractional order dynamics point of view for the complex system for complexity characterization and possible regulation. Okay, so you can tune that complexity or level if you want, sometimes, not always. So here's a summary of my key message today. Okay, the real worlds are complex. You agree already. Our human being perceive the complexity via our mental prism or lens or the calculus we use. Okay? So we might be limited by the calculus we use to understand the words around us. So basically, and from the outside, people again and again discover and rediscover the inverse power law from outside view at the microscopic level. So they keep discovering this. And in the 1990s, 1980s, if you discover something from the data of the inverse power law, you get Nature Science paper published. But not today. Okay. Today you need to learn another word called Mittag-Leffler. So we should actually call these things called Mittag-Leffler. I'll show you later. So you see some Chinese characters in here, and I'm saying that tail matters. Okay. I'm going to explain this one to you again. And this is from Tao Te Ching, you know, this Taoism, the text. And so everything that is hard to understand is in the tail. Okay. I'll go through that. So you agree that we understand the world through the lens we use, mental lens. Okay. So just go quickly, but you know, people do this. So I already showed you. So I'm not trying to criticize anybody. We'll agree that in front of a complex world, we are acting mostly like all these blind people here. You touch only part of it, so you draw a conclusion, say this is a wall or a rope or whatever. But it's understandable. But I hope everybody should agree that you probably only touch part of that. So let me show you. So I'm trying to tell you that fractional calculus should play a role, but it's unfortunate that there's like 10,000 page encyclopedia, and I searched the word fractional calculus. It's only appeared once from a person I know very well. I feel, wow, this is exactly showing this picture. Okay? Exactly, I'm showing you what I said here. They're touching the parts of the elephant. Okay? So, and there's also a book I like, and I searched the word fractional, it showed up 0 times. So then I decided I don't have to read this book. I mean, maybe you should read it, but he's basically answering why the 21st century isn't like the 20th century. So obvious. To understand that, you need fractional calculus, actually. Okay. So here is my theorem. Okay, if not axiom. Okay. Whenever you see power law, probably you should read it Mittag-Leffler law. Okay? Whenever we talk about power law, you actually are talking about fractional calculus. Whenever we talk about stretched exponential, then you're almost talking about fractional calculus. Okay. So, very interesting. Next slide is showing you that I taught ME 280 and fractional order mechanics, and during the lecture process, and I simply do the chalkboard writing lecture, and something emerged. Okay, something emerged. It's spontaneous coming out. I didn't plan to talk, so it's totally emerged. So I draw a bow tie and say this is understanding. So you can see there's a bow tie here. Okay, there's a bow tie in here, so you have something here, real world complex system phenomena. So I type it in neatly. I see this. So you have a complex system on this side of the bow tie going through the lens, which is inverse power law. Then you observe a lot of interesting macroscopic level behavior like scale-free, heavy-tailedness, long-range dependence, and long memory. Some of you may heard one of these, right? Okay. So, but this is just a microscopic behavior you observed, and you interpret this one as inverse power law. So to say, oh, then this is a complex system, complex behavior. That's what we have today. So what I'm going to convince you what we should have, okay? If we throw away the integer order calculus, then we're going to say, oh yeah, the complex system real world is fractional dynamic or in nature. It's actually like this. And then going through something I call Mittag-Leffler law, and using a fractional calculus-based models, then you see this, okay? Still you see this, but you gain more insights, So I want to explain why inverse power law should be replaced with Mittag-Leffler law, okay? So some of you never touched fractional calculus. This is the time to learn the basics. So let's talk about integer order calculus here. So it's also called exponential law. You do a first order differentiation. This is a relaxation constant. This is initial. So you decay, exponentially decay. So that's our integer order calculus. Of course, you can use multiple time constants and sigma them together. You can do a more complex approximation then. But there are some cases, no matter how you do the combination in here, you never be able to approximate nicely. I'll show you in a minute. So there are some physical phenomena. You have to use power law. So when we say power law, is the consequence of fractional order calculus. So let's do a fractional order differential equation in the simplest possible form with a constant driving term without damping. Okay, so then you will see that is t to the power alpha. So this is a Euler's gamma function as usual. So you can see the power function, do a fractional derivative, we'll get k minus alpha as usual, okay? But what if we have damping term? We have damping term in here. Things are more complicated. We need to use something called Mittag-Leffler function, which is a generalization of e to the power of x. So when alpha beta is 1, this EX then can be more general, alpha and beta in 2 parameters, okay? I'm going to show you next about this asymptotic behavior. So, but anyway, the exact solution of X under the fractional order relaxation is like this, okay? It's like this. Don't have to remember. So I have to say something about Mittag-Leffler. He's a wonderful person. If you use LaTeX, you will know that today's LaTeX, writing papers using LaTeX, is followed by Harvard professor Don Knopf, the creator of the text. And he initially referred to his journal about Acta Mathematica, okay? and that format, that fonts, that layouts, so on and so forth. Okay, so when you use LaTeX, then you should thank Mittag Leffler. And I heard his wife is very rich, so he's here. So he can concentrate on doing research. So. But anyway, it's funny. Mittag function has a connection of all special functions. In fact, the people I already read papers, and I know a person wrote a paper about saying that the Mittag function is the queen function of all functions, so that all the non-special functions you know, whatever, special functions could be generated by using Mittag function. So that's why you call it the queen function. And it has been implemented in MathWorks, MATLAB. So go there and you can download a copy. By the way, Igor Palumni visited us twice in the past 3 years. And if I draw, using the code and draw, I'm going to show you. So look at this one carefully, okay? So this is x. This is a Mittag function of minus x to the power of alpha. So you will see that when x goes to 0, so you can see this drops fast. This is Mittag drops fast, then decays slower. This is exponential, so then decays faster and faster, but initially slower than that. Okay, and in the middle is e to the power of square root of x is called stretched exponential. Stretched exponential. This is something in between. Okay, something in between. Okay, if we focus on here or here, so we can draw the conclusion that when x goes to infinity, it's a very large, then it is inverse power law. It's IPL, it's inverse power law. It is exactly why we see inverse power law all the time. But we forgot to study the details in here, because we observed those things. So whenever you do any research and you observe the power law, I would like to suggest you to think about fractional calculus immediately. Okay, immediately. So let me refresh your memory. It's important. Whenever you see inverse power law, in fact, what the bigger picture is Mittag-Leffler law. The real elephant is saying that the real world is fractional order way. Okay? Fractional order way. But of course, from outside microscopic level, everything you see is still like this is like behaviors at the microscopic level. You see scale-free, you see heavy-tailedness, you see long-range dependence and long memory, and so on and so forth. Okay, so power law. Okay, power law. So there's. I want to convince you that when we say power law, there are multiple things corresponding to that. One is called scale-free. In fact, when you say scale-free, you are saying power law. When you say power law, it already implies scale-free or scale invariant. So you can see this is called, if k is negative, it's called inverse power law. So this is inverse power law. And so then scale invariance, meaning you scale this x with c, you put c in here, and you get the same law out, and with a little bit of different coefficient. So it's still proportional to that. The law didn't change. That's important. That's important. That's why you zoom in and see the same at the different scale. See the same thing. It's not like exponential law. You change the scale, you change the law. Okay? So I suggest you check Chris Kello is our cognitive science professor on campus. Scaling laws in cognitive sciences. And there are many other good reviews. You can check it out. So it's everywhere. So power law is everywhere. It could happen in different contexts. Okay, this is an important slide. Okay, so in different contexts, so in the complex networks, you see scale-free about degree distributions versus degree. So that kind of scale-free network is a power law. You have pink noise in terms of power spectrum. It is power law. By the way, I remind you, pi law links to fractional order dynamics. But sometimes it's a probability density function, right? PDF. Okay, Gaussian it decays exponentially, but for algebraically it's different. So this inverse power law decay sometimes is also called algebraic decay, not exponential decay, or algebraic tail. And also happens in autocorrelation function ACF. So the distance tau versus your autocorrelation. So it decays not exponentially but algebraically. So that's another power law. And relaxation and evolution over time. This could be also very slow decaying. That's inverse power law. Anomalous diffusion in terms of MSD, mean square displacement versus time. Okay, and also self-similar is also a concept linked to a power law. So those are from physical quantities. You do an analysis, you will see the power law here and there all the time, because it shows up in a different contexts. But in the daily life, in the even higher level, that we see the connections is in a hidden way. So we see the geometrically it's fractal and it's irregular and it's anomalous and rough and so on and so forth. And in physics, I don't know much. And the renormalization idea is also due to power law. Talking about universality, all because of power law, you can say that. And in the extreme events, the spikiness or burstiness and the intermittence of events. So from stochastic point of view, then the PDF will follow the heavy-tailedness. And fluctuations, variabilities, like your heart. By the way, your heart never beat the same way, all right? Every two heartbeats are different. So those variability between heartbeats is called HRD, heart rate variability. Okay, then it's fractional order signal. Emergence, surprise, and black swan, all these are linked to fractional calculus. Non-locality, long-term memory, all linked to fractional calculus. And anything you use the word to say complex, that's linked to fractional calculus. Because when you say complex, then that means you have observed there's an inverse power or somewhere on some context. Okay? Okay, you heard about 2080 rule. You heard about it takes all kinds. So just to tell you that when the system is complex, you should not feel surprised you see anything. Okay? So that's why that explains in the physics so that people were talking again and again about power law. So today I hope I convince you to revisit that and take a look at fractional calculus so that you can see the whole elephant. Okay? I'm not saying you like a god, so that's not right. But fractional calculus will make you understand the bigger picture better. Okay? So the tail is important. Okay? Tail is important. So this is called exponential decay and exponential tail. This is called stretched exponential tail. This is called algebraic tail. Okay? And again, I try to promote the idea that we should understand our complex system, complex physics system, in such a way that by default it should be fractional order dynamic. And we should use fractional order based models to model it. And then we should check its tail behavior, which is shows up inverse power law. Okay. So this kind of fractional order calculus point of view, it's actually happens everywhere. And remember that when you were elementary and school kid, you were taught that x to the power of 10, then that means you have 10x multiplied together, right? But at some point you forgot that when you start to believe that x to the power of n, that n could be non-integer, right? Okay, so it's the same thing. We go in between integers. That's people saying that God invented integers. All the rest or invented by a human. Okay? And so, like, you go to, if you buy a cooker, rice cooker, you'll see there's a fuzzy neural inside. So it's basically fuzzy logic is going in between 0 to 1. Okay, 0 to 1. So you have logic, you have a membership function and stuff like that. But the idea is going in between, think in the fractional way. Okay, the fractional order splines, the fractional order moments, and fractional order dimension, and the fractional Fourier transformation, and in general fractional order calculus. All these things are connected. By the way, we should call it the non-integer order calculus, but it's historic reason we use fractional. What you should understand is a non-integer. Okay. Well, let me quickly show you on how useful it could be. Okay, I use something interesting for you. It's called complex relaxation in nuclear magnetic resonance, MRI. So you understand that the healthy and non-healthy tissues will respond to the transverse magnetization strengths will be different, like white matter, fat, gray matter, and so on and so forth. So checking the decaying of this magnetization strengths, relaxation process can tell us the change in the tissue, property change. So that's what they call the CPMG procedure to excite the tissue so that you can get a relaxation curve like this. So I call this is complex decay. Complex decay. So you say, oh, I know that. Let's fit it. So this is called D by Derby relaxation. Okay, so one constant. But question is, how do you know there's only one tau there? It could be infinite number of tau there, right? Could be. So that's why there's a guy in 1949, he said, yeah, let's talk about this. Let's do direct. Let's put an infinite number of low-pass filter in here and add a weight to them and add together. So instead of you get a constant tau, then you will get a curve, f of tau, a curve. So that curve probably is more indicative, can give you a better informed decision regarding diagnosis of cancer or whatever, or treatment response, so on and so forth. But the question is, can we go a little bit further? So you got to 1941 and Coe, I think the two brothers, and find out no matter how you try, you cannot really fit well in some cases, a very anomalous relaxation process. You cannot do that. You have to raise this guy to the power of alpha. The alpha is not 1 to be able to fit well, which is significant. And they made a historical position for themselves in the literature. So this is called co-relaxation. Co-relaxation. So me and my students, a few years ago, I say, oh yeah, let's fit this one. So I got alpha and a curve, so we can have a little bit more information, we can do better decision. So, but I confess I never read this paper. I never read this. I thought it's a significant generalization. But later on, I checked the literature and I found this 1949 paper on this. It's called the time constant distribution, so infinite number of time constants like that.
YangQuan?
Yes.
When you make this transition to this family,
Mm-hmm.
how many more parameters do you add, and how do you statistically address the superiority of fit given the increase in number of parameters? Is it like an information criteria?
Yeah, we have to stop somewhere. You know, you keep adding complexity in your model. Of course, you can do better, but we should stop at some point. You will not going to gain more insights when you add more tuning knobs or parameters there. So that's a very good question. We have to stop. There are some criteria we can apply so that you check the wideness of the residue. Those kind of questions can be addressed. It's answered in the system identification literature. There's something called AIC criteria, archaic information criteria, can be used to do that decision when I should stop adding more parameters into the model. Okay. That's why I can do more complex relaxation model. But the question is just like code everything. Some people generalize it. The raise R instead of raise S directed, the raise bracket beta, and the raise both. And I also can introduce all these things. So distributed order case, can we integrate over the order? Sure, why not? So because you keep hearing something, people say, oh yeah, observe the phenomenon that is scale rich. There's just so many scales. Okay, scale rich. Then probably you have to add an infinite number of orders in here, scale rich, to capture that. So I give you an illustration here, and I generate this data and try to fit. But suppose I don't know what is an alpha, then I try to scan alpha from 0 to 1, and this is the fitting error, so I say this is 0.75, exactly showed up. Don't you believe that this best fitted alpha will really give us some more information about your status of contraction of cancer or not? I don't know. I need real data. So it's your job. So if you gain a Nobel Prize or something, acknowledge today you heard from here. There are more things we can talk. And let me see my time. Yeah, got 10 minutes. Great. So you see that the noise and fluctuations everywhere, and these things are complex. The reason it is complex is because of those fluctuations are in a strange way. So they're called persistent or anti-persistent. So this normal Gaussian noise with this fractional Gaussian noise, fractional Brownian motion. So you can see they visually look very different. Okay, very different. Okay, and so those fractional noise, okay, is there. So whenever you have something to deal with noise, randomness, you start to think, I may have a chance here. So let me show you. There's a paper published on the Nature Against 2005, 10 years ago. Origin of births and heavy tails in human dynamics. Okay, so basically get some data, a lot of spiky, then check the inverse power law, PDF, probability density function. So those, if you have spikiness, burstness in your data, you should feel happy. I told you this inverse heart rate variability, so you can see the slope. Here, this is a spectrum, okay? So spectrum, so you can see the slope here is significantly different for healthy and sick people. So indeed, it's useful, fractional calculus here. But still, a lot of people were not well educated on the heavy-tailedness. It's because in our textbook, we usually don't teach stable distributions. So if you feel like your research is linked to randomness, stochasticity, you should go and educate yourself on stable distribution. So Gaussian, Levy, all these things are very simple case, okay? Cauchy, and these are the simple case. But there's a continuum of distributions. Okay, distributions. So I don't want to go too much details, but sometimes you can even write an explicit formula, analytic formula for the PDF. But only thing we know is governed by master equation like this. Okay, so fractional calculus and the stable probability distribution, 1998. Greenfellow and Francesco Mainardi wrote a very wonderful paper, tutorial nature. You will be able to appreciate that all the heavy-tailed PDFs are governed by a fractional order PDE like this. The solution will be the PDF function. Did I confuse you? Let's see this. So you have Gaussian, this blue is a Gaussian distribution, it's exponentially decaying. Okay, so it's something beyond 3 sigma, then you say it's very rare. Okay? But the red one is called Cauchy or some other. So you can see the tail is become, so this is much thicker than the blue. So it's also called heavy-tailed distribution. So heavy-tailed distribution. Okay. So if you do a log-log, you will see it much easier. So this is a Gaussian distribution. This is a polar decaying. So because of this thickness in here, we can see if by nature the PDF is heavy-tailed, then our mind is actually hard-coded with the blue line. So anything beyond 3 sigma we believe is rare. So that's why when we hear from news that extreme events are happening more and more often, right? Keep hearing this. That's because of this type of conflict in here. In your mind, you have a Gaussian distribution, but in reality, everything is extreme events are actually a heavy-tailed distribution. Agree? You probably will. But let's do something even more fun. Drop a ink into a bucket of water, so you'll see and it will disperse and fill in the space uniformly. I was supposed to stop, but I have 5 minutes. Okay, Brownian motion. So we will fill it up, but it could be leafy flights. So you can see there are a lot of holes in the space, not covered. Okay, not covered. So this is fractional. This is fractional noise. This is integer order. So obviously, in reality, I'm going to show you an example soon. So it's possible that this is not able to capture the complexity we see in the real world, while these we can. So we figured out a way, not me, somebody figured out a way to quantify the level of spikiness and the burstiness. So you can see I can generate different level of burstiness, okay? So because of that, we can use this fractional calculus as a tool to better quantify some complex phenomenon. For example, network traffic, okay? It's very fractional order in nature. So people using different ways to do it. But these things, you look at here, they are all related to fractional calculus, okay? If you do the complex network, and it's traffic, and other things, any man-made, any living things, any complex things, you should use one of these tools in here. Okay? Well, let's go quickly. Long-range dependence is in the context of autocorrelation function, and you can see long memory is like you have short memory, you have a disturb, it will decay quickly, but this one will decay slowly. So I'm going to go quickly, and so basically it's an autocorrelation function. Then it's the tail behavior is algebraic. Okay, this is a constant. This is mathematically saying that the tail behavior is algebraic. Under some assumption that we can also say the spectrum density obeys this inverse power law as well. So there are multiple things we can say that. So the heavy-tailedness is an important concept, okay? And it's linked to inverse power law of your PDF distribution. There's more than 100 years of study of long-range dependence and heavy-tailedness in terms of force. You probably heard some of these, like Zipf's law and stuff like that, everywhere. But we should ask, what's behind all this microscopic observation of this thing behind it? That's exactly the fractional calculus, fractional dynamics. So I have a simple example to show you the connection between long-range dependence, power law, and fractional calculus. Put on white noise and do fractional order integration, you generate an output, which is, of course, is a colored fractional noise. But if you do an output autocorrelation function, is inverse power law, and it's I'm going to close by telling you that our real worlds are complex. I should say our real physical worlds are complex because we are physicists. And our human being also perceive the complexity via our mental prism, and we need a tool or lens. And previously, people focused on the inverse power law, and if we use integer order calculus, and actually I told you we should consider Mittag-Leffler. And so those power law happens in different contexts, and anything you observe in a daily life, like surprise and emergence, extreme events, all these things, or the use of the word complex, you should immediately think about its possible connection to fractional calculus, although sometimes it's hidden. And so what really matters is the tail behavior. Pay attention. Okay. And Scott Blair already told us that we do what we do now is for our own convenience. Nature is not running that way. It's running in a fractional dynamic order way. So today we're here. So no matter how smart you are, before Newton Leibniz invented integer order calculus for you, you can only study static or geometry stuff. But today you can do more, do better in the complex words. Okay? And this is something you have seen. We now got a better range. Okay? So when you should use all these things, and it's called self-similar, skill-free, power law. Whenever you see any word inside here, you should link to fractional calculus immediately. So it's evolving, and so this is 2005. We have snapshot of this power law. But today I have something new to share with you. It's called new wisdom. Okay. So if you check into the Taoism and Tao Te Ching, and you will see this is Dao Ke Dao Fei Chang Dao. It means the nature's rule of complexity and could be explained by the non-normal way. So what is a non-normal way? It's a fractional calculus heavy-tailedness, a kind of fractional order way. So I'm done. Okay, here. So we keep saying that God is in the detail, devil is in the detail, whatever you check. But I would like to remove the DE. All the things are happening in the tail, actually. So you should go fractional, and it's quite urgent because other people will capture, and I see more and more people dive into the field. So do it. And if you want to do yesterday's science, you can keep doing what you are doing. If you want to do tomorrow's science, you should consider fractional calculus. This is the book. Will show up in November. You can buy a copy. I already have a copy, and in March edition. So it's called Fractional Calculus: View of Complexity, Tomorrow's Science. So do you want to do tomorrow's science today? Yes. Then you need fractional calculus, and expect the nice book. Okay. And I'm done. Yes, please.
Typically, when you see Taylor series of Lorentz, they have larger number of derivatives, but can you apply fractional calculus and make something like a continuous derivatives on functions and make a continuous Taylor series?
Are you talking about kernel function? Doing a...
Taylor series has like integer number derivatives, but can you change it to fractional derivatives?
There are efforts trying to do that generalization. Yeah, I noticed that, but it's not in the mainstream to rewrite that. So that they define the Laplace transform instead of using exponential lambda st, e to the power of st, they do Mittag-Leffler function st. So there's some obstacles I have to tell you mathematically. There are some wrong results in the literature. I know.
I had a practical question and a just theoretical question. The practical one is you showed some sort of toolbox for MATLAB for,
yes.
for the function.
Mm-hmm.
Is that an open access free library so it could run on Octave too?
I haven't tried.
Sure, okay.
Probably. MATLAB. So don't try to write any code related to fractional calculus. Ask me first. I'm serious. Don't duplicate effort. So.
My theoretical question was, you had a book by Salas up there, and I wondered if...
Yeah.
So the Salas entropies have a form that also has a exponential parameter, if I remember correctly.
Stretched exponential.
Yeah. Oh.
So e to the power of x to the power of alpha, that kind of thing. You know?
Yeah. So are there entropies that...
That's beginning. I think 2 years ago there was a paper on this fractional entropy definition. Try to do that. So I don't see any good results along that way of thinking. Probably, if you feel this can be useful, it is an interesting direction to generalize the definition of entropy. Maybe 2-3 papers already showed up in the past along this, what you said. Attempts. You should say something. You didn't know that this guy is doing fractional calculus all the time. He just don't want to tell us.
So I have my question was that, so the way it was presented, it's more a metaphysical question. So does it have explanatory power? So saying something, it can be described by fractional dynamics, it's fine. So I'll give you an example. For example, anomalous diffusion. So if you have continuous time random walks, it's say in a physical system you have traps or something like that. And then what will happen is, how do you get it to be described by a fractional order differential equation? The way you get it is if you assume that the trapping times are distributed in a power law fashion. So now you have fractional order calculus arising from a power law distribution of something else.
Yes.
So my question is, then you nest this infinitely. So at some point there needs to be a physical explanation. So my question is, you could say that everything is described by fractional order calculus, but does that give you insight into the system, like physical insight? Right?
So the Caltech physicist, what is the guy? Feynman said, you give me 4 parameters, I can fit an elephant and wiggling the tail for you. So simply fitting the model is not going to really work. That's why insights are very important. Physical insights are very important. So Rudolf Kalman, who invented the Kalman filter, by the way, and he said that, I heard he said that in 2005. He said, make physics right, the rest is mathematics. It's not opposite. You have to make physics right. So therefore, physical insights is very important. I suggest everybody look into that. But to address Professor Goibin's question regarding the generating mechanism at the microscopic level and how they have one-to-one correspondence. So in the macroscopic level, you have fractional order model, it fit nicely, and everybody's happy. But if you don't have a microscopic generating, I said generating mechanism to interpret that or to reproduce that, that's hard to convince people. So that's why if those traps are by design, that would be even more interesting. So you observe some sort of microscopic fractional order model, then you design some trapping mechanism or trapping distribution such that the microscopic, you observe exactly what you observe. I think that line of research is very interesting. And I already have seen people doing molecular dynamics, Monte Carlo, or whatever. If we bring this thinking into that, we'll add serious fresh blood into the research, like inspired by Professor Goibinathan. So I know you have some work on this direction, but think about the trapping as a designing freedom. What's going to happen? So what's the optimal trapping then? So
Yeah, in the paper, optimal actually net exponents for.
Nice. So what is the? Oh, yeah. Another question is because you open this tuning knob, the alpha, the order. So what is the best order? Okay. So you have to make a choice. Then what's optimal? And then you need to ask, what do you mean optimal in terms of what? So opens a lot of interesting research questions and opportunities. So, all right. Timing is okay. Okay.
So if there is no further question, let's thank our speaker.
Thank you.